Okay, so today we're going to focus on key characteristics of exponential functions, but here he begins with comparing linear, quadratic, and exponential functions. These are your Math 1 functions. These are the 3 functions that you look at in Math 1. But they keep coming back up over and over and over and over again, because whenever you go through the math classes, you keep adding functions to these, but they never go away, right? So you're going to keep using these over and over again. So exponentials are some of the most important in the real world. In Math 1, it's my favorite thing to teach because there's so many places it actually does apply. Things like he has listed here: population growth, money, interest, and debt, radioactive decay, spread of disease, all kinds of things that can be modeled with exponential functions. These also are some of the main functions that are featured on the SAT or ACT. So they show up a lot there, and I still use them even all the way up to calculus. So they're very important. Exponential is what we're focusing on today. So an exponential function has the general form a times b to the x power. B must be greater than 0. Whenever b is negative, you get these crazy graphs that switch back and forth from positive to negative and are no longer exponential growth and decay problems. In fact, let's go over Desmos, type 1 in. So I've got y equals 3 times negative 2 to the x power. What did it even do? It had some dots there. Look, it can't even do it. It doesn't even want to do anything. Sometimes it'll graph something crazy. I think the calculator will graph something crazy. So B's got to be positive. In this case, A represents the initial or starting amount. Okay? You can think for sequences, it's your a sub 0. Now, we're talking about functions, so we wouldn't call it a sub 0. It's not a sequence, but it's that starting amount. And B represents the growth or decay factor. We are mostly focusing, X is typically going to be time in most applications to the real world. So you can put a note about that. X is usually time in applications of the real world. There can be scenarios where it's not, but it is usually time. It depends on what they give you as the problem for that. So in general, when you want the equation, like you're typing it in to graph it, it will not have anything plugged in. But if they ask you for what is the amount at 6 hours, you would plug it in. Yeah. Exponential growth versus exponential decay. So if you have exponential growth, then your A value is positive. So your starting amount is positive, and your B value is greater than 1. And I don't think he puts this on here, so let's write it right here. I hope it lets me because this is a table. Your B value is going to be 1 plus the rate as a decimal. Okay, So if you have a 5% growth rate, you're going to change that 5% to a decimal, which is 0.05, and you're going to add it to 1. That will give you your growth rate for that. Notice A is positive in this case. So you're starting with some sort of positive amount there. Again, for exponential decay, A is going to be positive. I'm not aware of really like applications for these where A is negative. You definitely can have an equation where A is negative, but it'll flip the graph upside down, but it's not going to be we typically do not see that in applications in the real world, because normally we are starting with a positive amount of something. So for exponential decay, A again is positive, but B is between 0 and 1. So it is a fraction somewhere between 0 and 1. For exponential decay, B is going to equal 1 minus the rate as a decimal. So if you have a car that is depreciating by 15% every year, then you would do 1 minus 0.15 to get that B value that's there. Okay. Some of the things that we're going to talk about with exponential functions are some of the same things we've talked about with the other types of functions we've looked at so far. So we need to know about whether exponential functions are increasing or decreasing. The thing about exponential functions is they are either always increasing or they are always decreasing. Okay, so you will not see them switch from increasing to decreasing. If so, they're not exponential functions. This means they're not going to have maximums or minimums, because in order to have a maximum or a minimum, you are going to have to switch from increasing to decreasing. So they will never have absolute maximums or minimums or relative maximums or minimums for this. When you have growth, they'll always be increasing. When you have decay, they'll always be decreasing. For concavity, they are either always concave up or they are always concave down. They will never switch concavity. They have no points of inflection. Always concave up or always concave down. Typically, the ones that are used in real life situations are going to be concave up, because the two that you're looking at right here are typically the ones you see in real life situations. It is possible to have a negative A value which flips these upside down, and that will make these concave down. So it is possible to have a function that's concave down. They're just less likely to be used in real life situations. Okay. We also want to talk about end behavior for these, and end behavior is going to be a little bit different for these, because in polynomials our end behavior was always up or down, right? So we had either positive infinity or negative infinity. So for polynomials, our only two options were these first two options. Then when we did rational equations, we introduced the idea that it could be 0 or even a number, but they were always the same on both sides, right? So if we had a horizontal asymptote, it was the same on both sides, whether it was negative infinity or positive infinity. With exponential functions, one side is going to go to 0, and the other will either go to infinity or negative infinity for that. So we have these three different options that we're looking at. And what you really have to do is just picture what is happening for the function. So let's look at a few problems. Okay. So some of this you may just be asked to do from the graph. So if we are looking at the graph, If I want my left limit statement, that's going to be the limit as x approaches negative infinity of, they did not name this function. I am going to call it f of x right here so that I don't have, I got to have something there. I don't want a naked limit. All right, on the left side of this function, what does it appear that we are approaching? Looks like it's 0 because it has a horizontal asymptote. Exponential functions always have a horizontal asymptote. So if it looks like it's going to a line, assume it is that line. Okay. On the right, I would be looking at what happens as I move to the right for this function. So Alejandro, on the right, what's this one doing? What is happening to our y values as we go out to the right side? Positive infinity. Very good. Right, because it goes up on that end. You're always, yes, you're always, any limit, you're looking at what the y values do. Yep. Okay. All right, so if I look at b, let's call this one, we'll call this one h of x here. And so on the left side, I'd have the limit as x approaches negative infinity of h of x. And on the right side, I'd have the limit as x approaches infinity of h of x. So, Jericho, on the left, what's happening to this one? Very good. Approaching negative infinity because on that left side, your y values are going down. And Deanna, on the right side, what is happening to our y values on the right side of that graph? It's approaching 0. Very good. It is increasing, but these have horizontal asymptotes, so you don't go with positive infinity, even though it is going up because it's kind of leveling out for these. Okay? C does not give us a graph. It gives us an equation. So if I think about what this graph would look like, my starting amount here is 5. Okay? And should my graph be increasing or should it be decreasing? Is this exponential growth or is it exponential decay? It is decay. How do you know, Connor? Very good. Very good. That b is less than 1. So it's going to look like this here. Okay. So that b value tells you whether you're dealing with exponential growth or exponential decay, which is going to help you know what your end behavior looks like. So limit as x approaches negative infinity of, they call this one g of x, and limit as x approaches positive infinity of g of x. Okay, so Marley, on the left, what is this one doing? Very good, approaching positive infinity. And Alyssa, what about on the right? Going to 0. Very good. And for the ones I'm going to give you here, it's always going to be positive infinity, negative infinity, or 0. The only way to get a number other than 0 would be if this graph had been shifted like up or down. And that would mean you have like a plus 5 at the end that shifted it up 5. But I will probably not give you that without a graph tomorrow for that. I could possibly give it to you without a graph, but it would have it clearly shown there.
Are we going to do translation for these?
Maybe a little. The translations work the same as they work with any other function. So it definitely could show up. I can't remember how much we do with it. Can't remember. Yeah, nothing special. It follows all the same rules. Okay. Questions there? All right. For example, 2, we are asked about concavity and increasing or decreasing. So for A and B, we're just looking at those graphs. We do see in B, we see an example where it has been flipped upside down. We do not typically see that in real life scenarios, but we do see it. Actually, that scenario right there, I guess maybe this could be real life. This is what happens to you if you go get a credit card and spend money on it and never pay it off. This is what your bank account is, your credit balance there is doing. Negative, 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 more negative. So this could happen in real life. Try hard to make sure that does not happen to you in real life. Because do not go, I don't know if they still do it. There used to be like credit card companies, like they're signing you up to get a credit card, like in the middle of the brickyard at NC State. Like my husband said, they'd always be there. They didn't come to Meredith much, but to get you a credit card there in college, since you're broke and they know you need money and you're going to spend it like it's free money. Don't do it. It's not free money. It's expensive money. So yeah, it's terrible. Now I use my credit card all the time. But I pay it off at the end of every month. I just kind of use it like a debit card because it gets like points for stuff where you get like rewards. The credit card company sets a limit on it for you. I don't know. You could probably request for it to be lowered. Because I know I can request for it to be increased. But I know that very first credit card that my husband and I had, it had a $500 spending limit. That's all we could spend was $500. It did not do as much good. But be careful with some credit cards so you don't end up like graph B in college. Or any time in life. Sometimes you're in a hard spot, but you want to try not to ever. You'll be most financially stable if you never use a credit card. And well, I mean, you can use it, but you got to pay it off at the end of the month. They don't charge you interest if you pay it off at the end of the month. Especially if you're using this said credit card to buy a new purse or to. We had a friend in college that like financed the TV. Like people didn't have flat screen TV, like big flat screen TVs then. You couldn't get them for $300 at Walmart. They were like $1,200, and he financed one at Best Buy, and it was supposed to be 0% interest, but then he bought something else, and that wasn't, and he didn't make the payment. And anyway, I bet that TV cost him $4,000 by the time he was done paying for it. It was a terrible, terrible decision.
Wait, I have a question. How do you build credit without a credit card?
You can use one, just pay it off at the end of the month. If you keep a balance on it, it costs you money. If you could, like, I use mine all month. I buy groceries. I buy everything pretty much with my credit card. But when the bill comes at the end of the month, I pay the whole bill. I don't ever, because if you pay it at the end of the month, they don't charge you interest. It's only if you let it go to the next month that they do. So, yeah. So if you get one, you need to treat it like you have to pay it off at the end of the month, because you do not. Yeah, because they'll tell you even though you spent $2,000 this month, here's your minimum payment of $27. But if you make that minimum payment, you're just going to be it's not going to be good. Don't do it. Pay it off as quickly, preferably pay it off every month. But if not, you need to pay it off as quickly as you can, because the longer, they're charging you interest every single month, and it's high interest on credit cards, much higher than like a car loan or a house loan or something. So be careful with that. All right, let's keep going so we can get this done. For this one, here, Kendall, what have we got? Is this one concave up or concave down? Concave up. Is it increasing or decreasing? Decreasing. Very good. Peyton, what about B? Concave up or concave down?
Down.
Concave down. And increasing or decreasing? Decreasing. Concave down, decreasing. This is the credit card situation you do not want to get yourself into. Here. Now, C does not give us a graph, so we want to try to come up with a graph for it, right? Our starting value is 3, so on a graph we would start at 3. Is it going to be growth or is it going to be decay? That one's going to be growth, so it will look like this here. So for that one, Mason, concave up or concave down? Up, and increasing or decreasing? Increasing. This is what we want our bank account to look like. Concave up, increasing. There. Although that was hard. That would be really hard to pull off. Concave up and increasing is pretty hard to pull off. Okay. Last one here. Selected values of the function f are shown in the table above. Determine if f could be linear, quadratic, exponential, or none of these. So this is a little bit of a tricky problem. What's the first thing we need to always check if they give us a table? When you look at the x values, and this x value goes up by 5, up by 5, up by 5, up by 5. So this, we are increasing by equal length values. So that means we can look at what's happening to our y coordinates without having to consider the x coordinates in this case. If that is not the case, then it's going to be even more complicated for that. So here, from 3 to 5, that goes up by 2, and then up by 4, and then up by 8, and then up by, what is that? Let's see, 16. There. Okay, now definitely not linear because we don't see that all being a constant term. Let's look at our second difference to see what's happening, because the other option is I can see like I'm multiplying by a number, but can you multiply 3 by a number to get 5? Not a whole number, right? So it's not looking like it's exponential in that way. But if we look at our differences, look what happens here. This goes up by 2. This goes up by 4. This goes up by 8. Same pattern again, right? And I bet if we had more numbers, we'd see the same pattern. If I do it again, up by 2, up by 4. And I bet if we had more numbers, it'd be 8 next. So while the numbers themselves do not look exponential, the pattern that we're seeing in our differences does look exponential. This is, in fact, exponential. Now, I'm not multiplying by 2. 3 times 2 does not give me 6. But if I look at my differences, 2 times 2 gives me 4. 4 times 2 gives me 8. 8 times 2 gives me 16. It looks like I've got 2 to the x power. The function you're going to have here is going to be 2 to the x power plus 1 for that. So this is a situation where you'd have a shift up or down. So I'm giving this one to you to show you that sometimes you need to look at those differences, because while it doesn't look like there is a, it doesn't look like, oh wait, there's also a fraction there because this is not going up by 1. It's not exactly that. Let's just say it's shifted up 1. It would be 2 to the x plus 1 if the x's were going up by 1, but they're not. So it's just been shifted up by 1, but it's still exponential for that. So if you look at your differences and you're seeing this happen, it's still exponential even if it's been shifted. All right, so